The galaxies are all rushing away from us, and the reason defies common sense. This is the expanding cosmos paradox, the baffling reality that space itself is stretching, carrying everything along with it. We are used to thinking of the universe as a fixed backdrop for stars and planets, but it is actually a dynamic, growing fabric. In this video, you will gain a completely new way of seeing the cosmos, understanding how its relentless expansion reshapes reality itself. We will explore where this growth began and what mysterious force is now speeding it up. What does it feel like to live in a universe that is continuously outgrowing its own skin? For centuries, the cosmos was seen as a perfect, unmoving cathedral. Stars were fixed jewels in a velvet dome, and space itself was an absolute stage, unchanging and eternal. This was the universe as imagined by Isaac Newton, a vast stillness where celestial objects obeyed physical laws, but the backdrop itself was permanent. Philosophers and scientists alike operated under this assumption of a static cosmos, a realm without a beginning or an end in its fundamental structure. Our own Milky Way was thought to be the entirety of existence, an island universe containing everything. This view left no room for a cosmos that was born, that evolved, or that was actively growing. It was a comforting, stable picture, but it was incomplete. The first subtle cracks in this model began to appear not with a bang, but with patient observation. Astronomer Vesto Slipher, studying the faint light from spiral nebulae, noticed something peculiar. Their light was shifted toward the red end of the spectrum. This redshift was a potential clue, a signature of motion away from us, but without broader context, its revolutionary meaning remained hidden. The evidence was mounting, piece by piece, against a static universe. Each observation was a quiet tap, chipping away at the foundation of a millennia-old belief. This gradual accumulation of data set the stage for a collapse of the old worldview. Realizing how deeply ingrained the static model was makes the discovery that followed all the more shocking. It forces us to ask, what other fundamental truths about reality are we currently taking for granted? Then came Edwin Hubble, a man with access to the most powerful eye on the sky, the Hooker telescope. He was not just looking at stars, he was measuring the cosmos. His meticulous observations of distant galaxies revealed a pattern so consistent it could not be ignored. The light from these galaxies was systematically shifted to the red, a telltale sign that they were all rushing away from our vantage point. But the real shock was what happened the farther out he looked. A galaxy twice as far away was not just receding, it was receding twice as fast. This relationship, now known as Hubble's law, was the bulletproof evidence that shattered the static universe forever. The cosmos was not simply existing, it was actively growing. This was not like objects moving away through a stationary space. Hubble's data pointed to something far more bizarre. The very fabric of space between the galaxies was itself stretching, carrying them apart. A simple analogy helps make sense of this. Think of the universe as a loaf of raisin bread dough as it rises. Each raisin is a galaxy. As the dough expands, every raisin moves away from every other raisin. From any single raisin's perspective, all the others are fleeing, and the ones farther away appear to move faster because there is more expanding dough between you and them. This single insight rewrote our cosmic story. It provided the foundational pillar for the Big Bang theory, the idea that the universe erupted from a hot, dense beginning. But it also planted the seed for a deeper mystery, one that would only become clearer with time. If the universe is expanding, what does that growth feel like for us, living inside the rising loaf? The answer defies every intuition we have about how the world works. The balloon analogy offers a powerful way to visualize this cosmic reality. If you take a partially inflated balloon and draw several dots on its surface, you are creating a miniature universe. As you blow more air into the balloon, each dot grows larger and moves away from all its neighbors. No single dot is the center of the expansion. From the perspective of any dot you choose, all the others are retreating, and the ones that were farthest away to begin with appear to be moving the fastest. This is precisely what Hubble discovered about our cosmos. The galaxies are not simply flying apart through a pre-existing emptiness. They are being carried along as the very fabric of space itself stretches. This explains why every observer on any galaxy would see the same universal flight, forever dismantling the ancient idea that we occupy a privileged central position. Our home planet is just another dot on an unimaginably large inflating surface. Yet for all its clarity, this simple model has its limits. Our universe is a three-dimensional volume expanding in a way we cannot fully picture, not a two-dimensional surface. The balloon has a clear center inside it and a definite edge at its rubber skin, but the cosmos appears to have neither a center nor an outer boundary. It is a concept that strains our everyday intuition, which is built entirely on objects moving within a fixed space, not space itself actively growing. This elegant analogy gets us halfway to the truth, allowing us to grasp the how of expansion while hinting at a deeper, more complex reality operating behind the scenes. What unseen forces are actually stretching the cosmic canvas, and why is this process not slowing down as we might expect? This cosmic stretching leaves a distinct fingerprint on the light traveling across the universe, a signature we can detect and measure. The phenomenon is called redshift, and it acts as a cosmic speedometer. You have likely experienced a similar effect with sound. When an ambulance speeds toward you, its siren sounds high-pitched. The sound waves are compressed, bunching up as the vehicle moves in your direction. The moment it passes and races away, the pitch drops dramatically. The sound waves are now stretched out, their wavelengths growing longer. This is the Doppler effect, a fundamental property of waves in motion. Light behaves in a nearly identical way. When a galaxy is rushing away from us, the very fabric of space between us and that galaxy is stretching. This stretches the light waves traveling through it, shifting them toward the red, longer wavelength end of the spectrum. The faster the galaxy recedes, the redder its light appears. This is not a subtle effect. It is a direct and measurable shift that allows astronomers to calculate the velocity of distant objects with incredible precision. Yet there is a profound difference between the siren and the starlight. The ambulance is moving through the air, a fixed medium. The galaxy, however, is not simply moving through a static space. The space itself is growing, and the light is being stretched along with it. This is cosmological redshift, the true hallmark of an expanding universe, not just objects flying apart. By analyzing the specific rainbow of colors or spectrum from a distant galaxy, scientists can read this redshift like a cosmic barcode. It tells them not only how fast the galaxy is moving, but, through Hubble's law, also its immense distance from us. The most astonishing part is that this light is ancient, a fossil from billions of years in the past. When we observe a highly redshifted galaxy, we are looking back in time and seeing the universe when it was younger, smaller, and expanding at a different rate. This single measurement, the simple reddening of starlight, confirms the universe's dynamic growth and encodes its entire expansion history within it. But this historical record held a shocking surprise, one that would completely upend our expectations for the cosmos's future. This cosmic redshift points directly back to a single, monumental event, the Big Bang. The theory tells us that everything we see around us, every galaxy, star, and planet, originated from an unimaginably hot and dense state nearly 13.8 billion years ago. This was not an explosion in space, but an explosion of space itself, a rapid unfurling of the very fabric of reality from a point of infinite density known as a singularity. In that first fleeting moment, the universe was a seething, energetic soup, far too hot for atoms to even form. As space expanded, it also cooled, allowing matter to condense and coalesce over billions of years into the vast cosmic structures we observe today. The echoes of this violent birth are still detectable, a faint whisper of radiation that permeates all of space. This is the cosmic microwave background, a cool afterglow that paints the sky in every direction. Its discovery was the smoking gun, the definitive evidence that our universe did indeed have a hot, dense beginning. It is the oldest light we can see, a fossil from when the cosmos was just a newborn. Yet this powerful origin story immediately confronts us with profound puzzles. What could have possibly triggered such a beginning? The laws of physics, as we understand them, break down at the moment of the singularity. The question of what came before the Big Bang may not even have a meaningful answer, as time itself may have begun with that event. We are left contemplating a universe that seemingly came from nothing, expanding for reasons that defy our everyday logic. This initial expansion set the stage for everything to come, but the story of the cosmos's growth was far from over. A new and even more baffling chapter was waiting to be discovered, one that would reveal the expansion was not slowing down as everyone expected, but was instead beginning to accelerate. This faint cosmic whisper, the cosmic microwave background, is the oldest photograph of our universe. It is the cooled remnant of that initial fireball, now just a few degrees above the coldest temperature possible. This afterglow fills every cubic inch of space, a constant reminder of our hot, dense origins. Its discovery was a masterpiece of scientific serendipity. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, annoying hiss in their antenna. They tried everything to eliminate it, even cleaning out pigeon nests, but the noise remained. That irritating static was the echo of creation itself, a signal from a time when the universe was a mere 380,000 years old. At that moment, the cosmos had cooled enough for the first stable atoms to form, turning the opaque fog of charged particles into a transparent universe. The light that was finally set free has been traveling ever since, stretched and cooled by the expanding space it traverses, arriving at our telescopes as this faint microwave hum. This is our ultimate snapshot of cosmic infancy, but this baby picture is not perfectly smooth. When we map it with incredible precision using satellites, we see a tapestry of tiny temperature variations. These minute fluctuations are the cosmic seeds, slightly denser patches imprinted on the early universe, held just enough extra gravitational pull to eventually attract more matter. Over billions of years, these specks grew into the vast cosmic web of galaxies and galaxy clusters we see today. The entire structure of our modern universe was written into that first light. The uniformity of this background radiation, however, presents a profound puzzle. How could regions of the universe on opposite sides of the sky, which could not have possibly exchanged information or heat, be at almost exactly the same temperature? This cosmic uniformity hints that the early universe underwent a period of unimaginably rapid growth, a process called inflation that stretched a tiny, uniform patch into our entire observable cosmos. The CMB does not just confirm the Big Bang, it provides a detailed blueprint of the universe's composition, revealing the presence of mysterious components like dark matter and dark energy that shape its expansion. It is the foundational evidence that space itself is stretching, for the light has been redshifted over its epic journey. This ancient glow is the ultimate testament to a dynamic, evolving cosmos, a story of growth that began with a bang and continues to unfold in ways we are still struggling to comprehend. Just as we thought we understood the cosmic expansion, a discovery emerged that overturned our most fundamental expectations. For decades, the central question was not if the universe would keep expanding, but how quickly it would slow down. The collective gravity of all the galaxies pulling on one another should have been acting like a cosmic brake, gradually decelerating the universe's growth over billions of years. The only debate was whether there was enough matter to eventually halt the expansion and pull everything back in a big crunch, or if the universe would simply coast onward, expanding forever at a steadily diminishing rate. This was the logical prediction, the inevitable outcome of a universe governed by gravity. Then, in the late 1990s, two independent teams of astronomers made a shocking observation. By studying the light from incredibly distant stellar explosions known as Type I, a supernova, which act as standard candles for measuring cosmic distances, they found something impossible. The most far-off supernova were significantly dimmer than they should have been. This could only mean one thing. These ancient explosions were much farther away than anyone had calculated. The expansion of the universe was not slowing down at all. It was speeding up. The cosmos was not just growing, it was accelerating, as if some unknown, repulsive force was blowing space apart. This was the moment we met dark energy. The name itself is a placeholder for our ignorance, a label for whatever is causing this anti-gravity effect. We now believe this mysterious component makes up about 68% of the entire universe. Think about that for a moment. The stars, planets, and galaxies, everything we can see and touch, accounts for less than 5% of the cosmos. The rest is dark matter, and this dominant, unseen dark energy, a force that pushes the universe apart. It acts in direct opposition to gravity's attractive pull. While gravity works to bring matter together, dark energy works to stretch space itself, driving galaxies apart at an ever-increasing rate. This is the true heart of the expansion paradox. Our intuition tells us that if you throw a ball into the air, it will slow, stop, and fall back down. We expect the same from the cosmos, yet the universe is behaving like that ball, once thrown, suddenly and inexplicably shooting away faster and faster into the sky. So what could dark energy actually be? The leading idea revisits a concept from Albert Einstein himself, the cosmological constant. He originally introduced this term into his equations of general relativity to force a static universe, a move he later called his greatest blunder. But it turns out this constant could represent a fundamental property of the vacuum of space itself, an intrinsic energy that gives empty space a kind of springiness, causing it to repel. As more space comes into existence, more of this repulsive energy appears, leading to a runaway acceleration. Alternatively, dark energy might not be a constant at all, but a dynamic field that changes over time, a concept sometimes called quintessence. Its true nature remains one of the biggest unsolved puzzles in all of science. Its dominance today is what makes the expansion defy common sense, ensuring that the cosmic growth we observe is not a relic of the past, but an active, accelerating process happening right now. This discovery completely reshapes the ultimate fate of the cosmos, pointing toward a future of endless, lonely expansion, a cold and isolated end. So if dark energy is the force relentlessly stretching the cosmic canvas, what is holding the picture together? The answer lies in a second, equally mysterious component, dark matter. This invisible substance exerts a powerful gravitational pull, acting as the cosmic glue that binds galaxies and galaxy clusters into stable structures. Without it, the relentless expansion driven by dark energy would have torn the universe apart long before any stars or planets could form. The evidence for dark matter is everywhere we look, just not with light. We see it in the way galaxies spin. The stars on the outer edges of spiral galaxies orbit so quickly that, according to the visible matter alone, they should be flung off into the void. The fact that they are not tells us that each galaxy is embedded within a vast, massive halo of something we cannot see, a dark matter scaffold whose gravity is the only thing holding those fast-moving stars in place. We also observe its presence through a phenomenon called gravitational lensing. The immense gravity of a dark matter cluster bends the very path of light from more distant galaxies, warping and magnifying their images like a cosmic lens. This allows us to map the invisible skeleton of the universe, tracing the outline of dark matter by watching how it distorts the light traveling through it. This hidden matter makes up roughly 27% of the cosmos, more than 5 times the amount of normal matter. Its gravitational influence creates a delicate cosmic tug-of-war. On the grandest scales, dark energy dominates, pushing galaxies apart as space itself expands. But within local structures like our own Milky Way, the powerful gravity of dark matter overwhelms this expansion, holding everything tightly together. This is why we do not feel the universe stretching around us. Our solar system, our galaxy, and even our local group of galaxies are all gravitationally bound islands, stable against the rising tide of expansion. We are living within one of these protected eddies, while the broader cosmic river flows outward at an ever-increasing speed. The profound paradox is that we inhabit a universe shaped and dominated by 2 invisible entities, one pulling things together and the other pushing them apart. We are only just beginning to understand the rules of this hidden contest that dictates the fate of everything we see. Albert Einstein's quest for a static universe led him to insert a fudge factor into his own masterwork, an arbitrary term he called the cosmological constant. His equations of general relativity predicted a dynamic cosmos, one that should either expand or contract, but this clashed with the prevailing view of an eternal, unchanging heavens. To force the math into alignment with common sense, he introduced a kind of repulsive force, a mathematical counterbalance to gravity's pull that would keep the universe forever fixed and stable. Then came Edwin Hubble's bombshell, the definitive proof that the cosmos was not static at all, but rapidly growing. Confronted with this evidence, Einstein reportedly discarded the constant, calling it his greatest blunder. He had allowed his intuition for a steady state to override the elegant predictions of his own theory. The irony is almost poetic. Decades later, that very same blunder has made a triumphant return. The discovery of the universe's accelerating expansion demanded an explanation, and the leading candidate is none other than Einstein's cosmological constant, reinterpreted not as a fix for a static cosmos, but as a fundamental property of empty space itself. This concept suggests that the vacuum is not truly empty. It possesses a tiny, intrinsic energy density, a background hum of existence that exerts a negative pressure. As the universe expands and more space comes into being, this vacuum energy increases, pushing the fabric of reality apart even faster. It is a concept that defies common sense, like a spring that grows stronger the more you stretch it. This simple constant elegantly matches many of our observations, yet it raises profound new puzzles of its own. quantum physics predicts a value for this vacuum energy that is astronomically larger than what we observe. The measured strength of dark energy is so incredibly feeble, yet so dominant on cosmic scales that its precise value seems bizarrely fine-tuned. Why is it so small and yet not zero? This fine-tuning is one of the deepest mysteries in modern physics. The story of the cosmological constant is a humbling lesson in scientific progress. It shows how even our greatest geniuses can be misled by ingrained assumptions, and how ideas once abandoned can resurface to illuminate the darkest corners of our understanding. Einstein's so-called mistake now lies at the heart of our biggest cosmic puzzle, a permanent reminder that the universe has no obligation to conform to our expectations. This deep cosmic uniformity presents a profound puzzle known as the horizon problem. Why does the universe look the same in every direction? The ancient light of the cosmic microwave background reveals a sky of almost perfect uniformity, with temperatures varying by less than a fraction of a percent. This should be impossible. According to the standard Big Bang model, the universe simply has not existed long enough for heat or light to have traveled from one distant side to the other. These regions were forever beyond each other's cosmic horizons, completely causally disconnected. Think of two people standing on opposite sides of a vast, rapidly growing field. If they start too far apart, they could never shout loudly enough to agree on the temperature, no matter how long they waited, because the space between them is expanding faster than the sound of their voices can travel. In the young cosmos, light itself faced this same limitation. There was not enough time for these separate patches of the universe to communicate and settle on a common temperature. Yet the cosmic background radiation shows they did. This is like walking into a vast, crowded room where millions of people who have never met are all wearing exactly the same outfit. It defies all expectation. How could such perfect coordination occur without any means of communication? The solution required a radical rewrite of the universe's earliest moments. The leading answer is a concept called cosmic inflation. This theory proposes that a tiny fraction of a second after the beginning, the universe underwent a growth spurt of almost incomprehensible speed. For a fleeting moment, a patch of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe. This explosive expansion happened faster than the speed of light. It is crucial to understand that nothing was moving through space faster than light. Instead, space itself was stretching, carrying that initial tiny region along with it. This process smoothed out any primordial wrinkles or temperature differences, ironing the cosmos into the uniform sheet we see imprinted on the CMB. Every part of our observable universe was once crammed into that infinitesimal, connected patch, allowing it to reach a uniform temperature before being blown apart. Inflation solves the horizon problem by giving the entire cosmos a shared childhood, but this elegant solution comes with its own staggering implications. What kind of energy could possibly power such an extreme event? The mechanism that triggered and then halted inflation remains one of the most active and speculative areas of physics, a hidden chapter in the universe's first moments that set the stage for everything to come. This flatness is not just a geometric curiosity, it is a cosmic tightrope walk of unimaginable precision. The universe's geometry is balanced on a knife edge, so flat that parallel lines will never meet or diverge but travel forever in unison. This exquisite balance depends entirely on the density of matter and energy in the cosmos. There is a specific critical density required to achieve this perfect flatness. If the actual density were even slightly higher, the collective gravity would have already halted the expansion and pulled everything back into a fiery big crunch. If the density were just a tiny bit lower, the universe would have expanded so rapidly that galaxies and stars could never have formed. The problem is that in an expanding universe, any small deviation from this perfect balance should have been wildly amplified over billions of years. Think of trying to balance a pencil perfectly on its tip. For a fleeting moment you might succeed, but the slightest breath of air, the tiniest vibration, will inevitably knock it over. The universe has been standing for nearly 14 billion years. According to our models, for it to still appear so perfectly balanced today, its initial density must have been fine-tuned to within 1 part in a million trillion at the moment of the Big Bang. This level of precision is like throwing a dart from one side of the observable universe and hitting a bull's eye just a millimeter wide on the other side. Such perfection seems astronomically improbable, a cosmic coincidence that defies all logical expectation. Why does our universe exhibit this seemingly impossible flatness? The answer, once again, points back to the dramatic growth spurt of inflation. In its first fleeting moments, the universe underwent that phenomenal stretching, smoothing out the cosmic fabric so thoroughly that any original curvature was effectively ironed flat. Just as blowing up a balloon makes its surface appear flatter and flatter from the perspective of a tiny ant crawling on it, inflation stretched our entire observable cosmos from a subatomic speck to a macroscopic size, rendering its geometry indistinguishable from perfectly flat. This elegant solution resolves the fine-tuning puzzle, but it simultaneously pushes our curiosity back to the very beginning. What set the conditions for inflation itself? Why did the universe start in that special, smooth state that allowed inflation to produce the flat cosmos we inhabit? This fine-tuning problem forces us to confront the possibility of deeper principles or even a multiverse, a vast landscape of universes with different properties where we simply happen to live in one capable of supporting life. The flatness of our universe is not a lucky accident, but a fundamental clue written into the fabric of space, a silent testament to the strange and precise mechanisms that brought our reality into being. This brief but spectacular moment of inflation fundamentally rewrote the universe's opening chapter. In the tiniest sliver of a second, before the universe was even 1 second old, a repulsive gravitational field, driven by a hypothetical entity called the inflaton field, took hold. Think of space as being filled with a strange, high-energy state that generated a powerful outward push, a kind of anti-gravity. This caused the cosmos to not just expand, but to inflate exponentially, doubling in size again and again at a rate far beyond the speed of light. A region smaller than a single proton was stretched to a size larger than our entire observable universe in a time too short to comprehend. This unimaginable growth spurt is what solved the cosmic puzzles of horizon and flatness. It took a tiny, connected patch of space and stretched it so enormously that it became our entire visible cosmos, explaining its perfect uniformity. It also stretched the fabric of space so thin that any original curvature was flattened out, just as blowing up a balloon makes its surface appear perfectly flat to an ant. But inflation did more than just smooth and flatten the universe, it also gave it structure. Even in that ultra-smooth early cosmos, quantum fluctuations were inevitable. On the smallest scales, tiny, random jitters in energy were constantly flickering in and out of existence. As space inflated at a fantastic rate, these microscopic ripples were stretched to macroscopic proportions, frozen into the fabric of space-time as minute differences in density. These tiny imperfections became the cosmic seeds, the gravitational anchors around which all future structure would form. Every galaxy, every cluster, and the vast cosmic web itself grew from these quantum whispers amplified to a cosmic roar. This elegant theory provides a coherent narrative for the Big Bang's immediate aftermath, explaining why the universe looks the way it does. Yet for all its success, the mechanism remains deeply mysterious. What exactly is the inflatoned field, and what triggered its sudden dominance and then its decay into the hot plasma of the standard Big Bang? Various models propose different answers, suggesting different durations and energies for this explosive growth. This transforms our understanding of cosmic expansion, revealing it was not a steady, gentle process but a story of fits and starts, of violent acceleration followed by a more stately pace. Inflation underscores that the universe's growth is governed by dynamic, shifting processes that defy our simple, linear expectations. If the very largest structures we see originated from the smallest possible fluctuations, what other profound connections between the quantum and the cosmic are waiting to be discovered? The implications of inflation stretch far beyond our cosmic horizon, into a territory that challenges the very definition of reality. If the theory of eternal inflation is correct, then the explosive growth that shaped our universe may never have truly stopped. Instead, it might be a perpetual engine, continuously spawning new regions of space-time that pinch off to become separate, self-contained universes. This is the Multiverse Hypothesis, a staggering idea that our entire cosmos is just one bubble in an endless, frothing sea of universes. Each of these cosmic bubbles could have formed with a random set of physical laws and fundamental constants. In some, gravity might be repulsive, or the strong nuclear force too weak to bind atoms. In others, space may have 11 dimensions instead of our familiar 3. Our universe, with its precise balance allowing for galaxies, stars, and life, would then be no grand design, but simply a fortunate accident, a single lottery ticket in an infinite cosmic draw. This directly addresses the profound fine-tuning we observe. Why are the constants of nature so perfectly calibrated for complexity? In a multiverse, there is no why. We simply find ourselves in one of the rare universes where conditions are just right, a concept known as the Anthropic Principle. The expansion we measure, the dark energy we puzzle over, and the very flatness of space become local by laws relevant only within our own bubble. This stretches the concept of cosmic growth to its logical extreme. The expansion of our universe is not the main event, but merely a small, ongoing process within a much vaster, perhaps infinite, meta-reality. While this idea currently lies at the frontier of testable science, it represents a profound shift in our perspective. It forces us to consider that the common-sense paradox of our growing universe might be a trivial detail in a much grander, more bizarre tapestry of existence. What does it mean for our place in the cosmos if we are not just a pale blue dot, but a pale blue dot in one of countless cosmic islands? A dark night sky seems like the most natural thing in the world, but this simple fact is one of the universe's greatest deceptions. For centuries, astronomers wrestled with a puzzle known as Olbers' paradox. If the universe is truly infinite, eternal, and filled with an endless number of stars, then every single line of sight you trace out into the heavens should eventually land on the surface of a sun. The entire night sky should be a solid, blinding sheet of light, as bright as the surface of a star. Yet when we look up, we see blackness punctuated by pinpricks. The paradox forces a profound choice. Either our assumptions about the cosmos are completely wrong, or we are missing a fundamental piece of the puzzle. The resolution lies in the very expansion we have been exploring. Our universe is not static and eternal in the way required for a bright sky. It has a birthday. Because the cosmos is only about 13.8 billion years old, light from stars beyond that cosmic horizon has simply not had enough time to reach us. We are surrounded by a shell of observable space, and beyond that wall is only darkness, not because stars do not exist there, but because their light is still in transit, racing across an ever-widening gulf. The expansion of space itself provides the second, crucial part of the answer. Even the light that does manage to reach us from the most distant galaxies is fundamentally altered by its journey. As space stretches on vast scales, the light waves traveling through it are stretched too, shifting them to longer, redder wavelengths. This cosmological redshift does more than just change the light's color, it also saps its energy. A photon of light that started its journey as visible, brilliant starlight can be redshifted into the invisible infrared, or have its energy diluted so much that it contributes almost nothing to the brightness of the sky. The universe acts like a cosmic dimmer switch, turning down the brilliance of distant objects. Furthermore, stars themselves have not been shining forever. They are born, they live, and they die, meaning the cosmos has not had infinite time to fill up with light. This beautiful convergence of ideas, the finite age of the universe and the energy-draining effect of expansion, resolves the ancient paradox. The darkness above our heads is not an empty void. It is an active, dynamic phenomenon. It is the signature of a cosmos with a beginning, a cosmos that is growing and stretching, carrying the most distant sources of light away from us faster than their brilliance can ever hope to catch up. The simple, profound blackness of the night is our most direct, everyday evidence that we live in an expanding universe, a universe whose growth defies our deepest intuitions about how reality should be. The ultimate destiny of our cosmos is written in the nature of dark energy itself. One possible future is known as the heat death, a slow and chilling finale. In this scenario, the acceleration we observe today continues at its current, relentless pace. Billions of years from now, the last stars will exhaust their fuel and wink out of existence. Galaxies will drift ever farther apart, their lights fading until the sky is utterly black. Over trillions upon trillions of years, even black holes will evaporate, leaving behind a universe that is cold, dark, and almost perfectly uniform. This is not an end in fire or ice, but in a profound and irreversible silence, a state of maximum entropy where no energy can be harnessed for any work or life. It is a fate of eternal isolation, yet there exists another, far more violent possibility, the Big Rip. This outcome arises if dark energy is not constant, but instead grows stronger over time. In this speculative future, the repulsive force would eventually overcome every binding force in the universe. First, it would tear apart galaxy clusters, then individual galaxies. The relentless expansion would then rip stars from their solar systems. In its final moments, planets would be shredded, and then atoms themselves would be pulled apart, dismantling the very fabric of matter. The universe would end not with a whimper, but with a catastrophic disintegration of space-time. Our current observations, measuring the acceleration of supernova and the large-scale structure of the cosmos, currently point toward the heat death. The strength of dark energy appears consistent, not strengthening enough to cause a big rip in the foreseeable future. But the unsettling truth is that we do not know this for certain. The precise properties of dark energy remain one of physics' greatest unknowns, leaving the door open for a more dramatic end. These two endpoints challenge our most fundamental narratives. We are accustomed to stories that conclude with a bang, a final, climactic event. The cosmos, however, seems to be writing a different kind of story, one where the end is either a slow, inexorable fade to black or a sudden, fundamental unraveling. Both fates hinge on a delicate balance, a cosmic tug-of-war between the outward push of dark energy and the inward pull of gravity on the grandest scales. The fact that this entire cosmic story, from the Big Bang to its final chapter, is governed by an invisible force we are only beginning to probe. Forces a humbling perspective. Our entire reality, from the largest galaxy to the smallest atom, is subject to the rules of this hidden contest. What does it mean for our fleeting moment of consciousness to exist in a universe whose ultimate fate rests on the behavior of something we cannot see? The very fabric of our reality is woven from randomness. On the smallest imaginable scales, the quantum realm is never truly still or empty. It is a seething ocean of potential, where pairs of virtual particles spontaneously blink into existence and then annihilate each other an instant later. These are quantum fluctuations, tiny, temporary jitters in the energy density of what we call empty space. In a static universe, these events would be fleeting and insignificant. But our universe is anything but static. During that explosive period of inflation, when space expanded faster than light, something miraculous happened to these quantum whispers. The universe stretched so rapidly that these microscopic ripples did not have time to simply vanish. Instead, they were stretched, frozen, and imprinted directly onto the fabric of spacetime itself. What was once a subatomic flicker became a macroscopic variation in density, a subtle hill or valley in the smooth early cosmos. These minute imperfections, these cosmic seeds, are the origin of everything we see. The slightly denser regions had just a little bit more gravitational pull. Over billions of years, they acted as anchors, drawing in surrounding matter, growing steadily from tiny seeds into the vast cosmic structures of today. Every galaxy, every cluster, and the immense filamentary web connecting them all can trace its lineage back to these random quantum events. This is perhaps the most profound connection in all of physics. The random, probabilistic rules of the quantum world, governing the impossibly small, were magnified by cosmic expansion to dictate the architecture of the entire universe. We expect grand structures to have grand, deliberate causes, yet the distribution of galaxies across the sky is fundamentally the result of ancient, subatomic chance. This process also reveals a hidden unity in the laws of physics. Cosmic expansion acts as a cosmic amplifier, a bridge that links the two great but often incompatible theories of modern physics. Quantum mechanics describes the bizarre rules of the very small, while general relativity describes the gravity and geometry of the very large. For the most part, these two worlds operate independently. But in that first fleeting moment of inflation, they became inextricably linked. The quantum provided the raw material, the random seeds, and the relativistic expansion of spacetime provided the mechanism to blow them up to a cosmic scale. Without this partnership, the universe might have remained a perfectly smooth, featureless soup of particles, a realm with no hills or valleys, no stars, no planets, and no one to wonder about its origins. The fact that we are here to observe a structured cosmos is a direct consequence of those primordial quantum jitters, stretched across the heavens by the universe's own incredible growth. Just when we thought we had a handle on the universe's expansion, a subtle crack has appeared in our most precise measurements. This is the Hubble tension, a stubborn discrepancy that challenges the very foundation of modern cosmology. On one hand, we have the cosmic distance ladder, a meticulous method using pulsating stars and stellar explosions in nearby galaxies to measure the current expansion rate, known as the Hubble constant. These observations paint a picture of a universe expanding at a specific, surprisingly brisk pace. On the other hand, we have a pristine snapshot of the infant universe, the cosmic microwave background. By studying the subtle patterns in this ancient light with incredible precision, we can use our well-tested model of cosmic evolution to predict what the expansion rate should be today. The problem is, these two gold standard methods do not agree. the local universe seems to be expanding faster than the early universe's conditions predict it should. This is not a large, glaring error, but a small, persistent tension that has withstood years of re-examination and improved data. It is a whisper from the cosmos that something in our accounting might be wrong. This tiny gap between measurements hints at a potentially vast gap in our understanding. Perhaps dark energy is not constant as we have assumed, but is evolving, growing stronger over time. Maybe there are unknown types of neutrinos or other exotic particles, subtly influencing the expansion history. Some physicists even speculate this could be a sign that Einstein's theory of gravity itself needs modification on the largest cosmic scales. The Hubble tension forces us to confront the unsettling possibility that our standard model of cosmology, for all its remarkable success, is incomplete. It is a puzzle that connects the very large to the very small, suggesting that the key to understanding the universe's overall growth may lie in the physics of elusive, undiscovered components. Resolving this discrepancy is not just about getting two numbers to match. It is a rigorous empirical test that could crack open the door to entirely new physics, revealing a cosmos even more complex and wondrous than we currently imagine. The universe whispers its secrets not only in light but in the very shudder of space itself. These are gravitational waves, ripples in the fabric of space-time first predicted by Albert Einstein. They are generated by the cosmos's most violent events, like the cataclysmic merger of two black holes. When such an event occurs, it sends literal waves through the four-dimensional continuum, stretching and squeezing space as they pass through. We have only just begun to detect these tremors with observatories like LIGO and Virgo, feeling the faint echoes of collisions that happened millions of years ago. But these waves are more than just cosmic curiosities. They carry encoded within them a pristine record of their journey. As a gravitational wave travels across the universe, the space it moves through is expanding. This stretching of the cosmic fabric subtly alters the wave's properties over its immense journey. By carefully analyzing these changes, scientists can use gravitational waves as a brand new, independent ruler to measure the universe's expansion rate. This offers a direct check on the Hubble constant, completely separate from the methods that rely on starlight or the ancient cosmic microwave background. It is like having a second, completely different witness to a cosmic crime, one whose testimony is not influenced by the same potential biases. The future of this field is even more breathtaking. Projects like the Laser Interferometer Space Antenna, or LISA, aim to launch a fleet of spacecraft into orbit, creating a gravitational wave observatory of unprecedented sensitivity in the quiet of space. This could allow us to detect the faintest whispers of all primordial gravitational waves generated in the first instance after the Big Bang. These waves would be a direct snapshot of the universe during its inflationary growth spurt, a fossil imprint from the moment the cosmos was stretched smooth. Detecting them would be like hearing the echo of creation itself, confirming the violent expansion that set the stage for everything. This multi-messenger approach, combining the traditional study of light with the new science of listening to space-time ripples, provides a more complete picture than either could alone. It is the difference between watching a silent movie and experiencing one with a full, immersive soundtrack. The subtle tensions in our measurements, like the Hubble tension, may finally be resolved when we can both see and hear the universe's expansion simultaneously. This new window onto the cosmos reveals that space is not a static stage, but a dynamic, vibrating entity, and its quiet hum holds the keys to understanding its deepest mysteries. Our very existence in this cosmos is a powerful clue to its nature. This is the core of the Anthropic Principle, a simple yet profound idea that our presence as observers necessarily selects for a universe capable of producing us. The expansion rate of the cosmos is a perfect example. If the universe had expanded just a little faster after the Big Bang, matter would have been spread too thin. The gentle gravitational tugs that pulled gas together into the first stars and galaxies would have been too weak, overwhelmed by the relentless outward rush. The cosmos would be a cold, dark, and empty void without a single star to light the darkness. Conversely, if the expansion had been just a little slower, the collective gravity of all that matter would have quickly reversed the growth. The universe would have collapsed back in on itself in a fiery big crunch, long before life could ever emerge on any world. We find ourselves, then, in a universe with an expansion rate that sits within a remarkably narrow window, a sweet spot that allows for the formation of galaxies, stars, planets, and ultimately, beings who can look up and wonder why. This principle does not explain the mechanism behind this fine-tuning. It does not tell us why the cosmological constant has its specific, curiously small value. Instead, it reframes the question. In a vast multiverse where countless cosmic bubbles inflate with different laws and expansion rates, it is no surprise that we find ourselves in one of the rare, hospitable ones. Our observation of this particular expanding universe is not a random accident, but a fundamental selection effect. Critics understandably point out that this reasoning can sound circular. Of course, we live in a universe that can support life because here we are. Yet this perspective offers a powerful shift in how we view our place in the cosmos. It connects the grandest scale of cosmic evolution, the relentless stretching of space, directly to the possibility of our own local, fleeting awareness. The fact that we are here to measure the Hubble constant and ponder dark energy becomes a meaningful data point in itself. It challenges the common sense expectation that the universe should exist independently of our observation, suggesting instead that the act of observation is woven into the fabric of reality we are trying to understand. What other cosmic mysteries might be solved when we consider that the observer is an inseparable part of the system being observed? These ghostly particles are streaming through you by the trillions at this very moment, completely unnoticed. Neutrinos are among the most elusive inhabitants of the cosmos, so reluctant to interact with normal matter that they pass through entire planets as if they were empty space. Born in the nuclear hearts of stars and the violent chaos of the Big Bang, they carry no electric charge and possess a mass so vanishingly small it borders on the non-existent. For decades, they were thought to be entirely massless cosmic phantoms that simply did not count in the grand ledger of the universe. But we now know they possess a whisper of mass, and in the vast scales of cosmology, even the faintest whisper, when multiplied by a near infinite number of particles, can shape the destiny of the cosmos. Their collective gravity, subtle as it is, contributes to the total energy density of the universe, a key factor that governs how fast space can stretch. This challenges our most basic intuition that only the most dominant, obvious forces drive cosmic change. It reveals a universe where the most silent players can hold profound influence. In the searing heat of the early universe, neutrinos were anything but passive. They moved at velocities indistinguishable from the speed of light, a relentless, high-energy wind blasting through the primordial soup of particles. This frenetic motion had a direct impact on the cosmic seeds we discussed earlier, the tiny density fluctuations that would one day become galaxies. The pressure from these light-speed neutrinos smoothed out the very smallest of these ripples, effectively ironing out minor wrinkles in the infant cosmos. This left a distinct signature on the large-scale structure of the universe, a subtle suppression in the clustering of matter on certain scales that is forever imprinted in the cosmic web. and in the detailed pattern of the cosmic microwave background. We can see the ghostly hand of neutrinos in the empty spaces between galaxy clusters, a fossil record of their early dominance. Their relentless motion meant that, for a time, they behaved not like matter, but like radiation, pushing outward and influencing how structures could begin to form. A pivotal shift occurred as the universe continued to expand and cool. The energy of individual neutrinos dwindled, and they began to slow down, transitioning from radiation-like particles to matter-like particles. This was a crucial cosmic handover. During the universe's first few tens of thousands of years, the energy density was dominated by radiation, which includes light and these ultra-fast neutrinos. This radiation-dominated era dictated a specific, rapid pace of expansion. But as neutrinos slowed and began to behave more like matter, their gravitational influence shifted. They began to clump ever so slightly in the gravitational wells of dark matter, adding their tiny weight to the process of structure formation. This transition helped usher in the matter-dominated era, which dramatically slowed the universe's expansion rate, allowing gravity to patiently build the galaxies we see today. The entire timeline of cosmic growth, therefore, carries the subtle fingerprint of this neutrino transition, a change in state that helped sculpt the universe from a smooth primordial fire into a structured cosmos. Today, the quest to pin down the precise properties of neutrinos is more urgent than ever. Their exact combined mass remains one of the most important unsolved problems in physics, with profound implications for cosmology. We know the combined mass of all three neutrino types is minuscule, but we do not know its exact value. This uncertainty is not a mere technicality. The total gravitational pull from all the neutrinos in the universe affects how quickly cosmic structures form and how fast the universe expands overall. Even a tiny adjustment to the neutrino mass in our cosmic models can shift the predicted expansion rate, potentially bridging the stubborn gap of the Hubble tension. Sophisticated experiments deep underground like Super Kamiok and in Japan, and precise observations of the cosmic microwave background from space are closing in on this mystery. They aim to measure the subtle ways neutrinos oscillate between their different types and to detect their imprints on the largest structures in the universe. By hunting these cosmic phantoms, we are not just studying particle physics. We are reading a hidden chapter in the story of cosmic expansion, one written in the faintest of ink. The universe continues to remind us that to understand its grandest motions, we must first learn to listen to its quietest voices. Measuring these immense cosmic distances requires a tool of extraordinary precision, a carefully constructed device known as the cosmic distance ladder. At its base on the lowest rung lies the method of parallax, a principle you can test by holding a finger up and closing one eye at a time. Your finger appears to jump back and forth against the background. Astronomers apply this same idea on a grand scale, observing how a nearby star seems to shift its position against more distant stars as Earth orbits the Sun. This simple geometric trick gives us a direct, reliable measurement for stars within a few thousand light-years, establishing the first crucial step upward. To reach beyond our galactic neighborhood, astronomers need a brighter beacon, and they found one in the rhythmic pulse of Cepheid variable stars. These special stars brighten and dim with a clockwork regularity that is directly tied to their true, intrinsic brightness. By measuring how long it takes a Cepheid to complete one pulse cycle, astronomers can calculate its actual luminosity. Then, by comparing that known brightness to how dim it appears from Earth, they can calculate its distance with remarkable accuracy. This is like knowing the exact wattage of a light bulb. By seeing how faint it looks from far away, you can work out precisely how far away it must be. Cepheids become the second, essential rung on the ladder, allowing us to measure distances to other galaxies for the first time. The next and most powerful rung extends our reach to the edge of the observable universe. For this, astronomers rely on cosmic explosions of such predictable power that they are known as standard candles. These are Type 1, a supernova, the titanic detonations of white dwarf stars. Because these explosions always happen at a specific critical mass, they always release the same staggering amount of light. When one of these events is spotted in a distant galaxy, astronomers already know its true peak brightness. The only reason it appears faint to us is the vast distance its light has traveled and the stretching of space it has endured along the way. By meticulously climbing this ladder, calibrating each step with the one below, scientists can measure the distances to these supernovae with confidence. It was this very process that led to the shocking discovery of dark energy. By observing that the most distant, and therefore ancient, supernovae were fainter than expected, astronomers realized the universe's expansion is not slowing but accelerating. This entire intricate structure is a testament to scientific rigor, a multi-stage verification process designed to root out error. A miscalculation on the first rung of parallax would ripple upward, distorting our measurement of Cepheids, which would in turn throw off our understanding of supernova, ultimately leading to a false picture of cosmic expansion. The cosmic distance ladder transforms the abstract, mind-bending concept of an expanding universe into hard, quantifiable data, one careful step at a time. It reveals a cosmos whose growth is not just a historical fact, but a dynamic and accelerating present-day reality. This staggering mismatch between prediction and reality is known as the Vacuum Catastrophe. According to our best theories of quantum mechanics, the empty space between stars and galaxies should be a seething, energetic foam. At the tiniest scales, pairs of virtual particles and antiparticles are constantly blinking into existence and vanishing again. A quantum fizz that should endow every cubic centimeter of nothingness with a tremendous energy density. The math behind this is robust and well tested in other contexts. Yet when we measure the actual energy of the vacuum by observing the universe's expansion, we find a value that is not just small but almost zero. The predicted energy and the observed energy are separated by a factor of 1 followed by 120 zeros. This is not a small rounding error. It is the largest discrepancy in the entire history of science. It means our understanding of the small-scale quantum world is fundamentally at odds with our understanding of large-scale cosmic gravity. One of these pillars of physics must be wrong or at least incomplete. The sheer magnitude of this error is a glaring signpost pointing toward a deeper layer of reality we have yet to uncover. If the vacuum energy were anywhere near its predicted strength, the repulsive force would have been so immense that it would have blown the infant universe apart in a fraction of a second. Not a single atom could have held together, let alone an entire galaxy. The fact that we exist to contemplate this problem is direct proof that the vacuum energy is, for reasons we do not understand, almost perfectly cancelled out. This is the ultimate fine-tuning problem. It appears as though some mysterious mechanism, perhaps a symmetry in the laws of physics we have not yet discovered, is quietly subtracting away nearly all of this vacuum energy, leaving behind only the faintest whisper we now call dark energy. This whisper is weak enough to allow for the formation of all cosmic structure, yet strong enough to now dominate the expansion of the cosmos. The vacuum catastrophe is not an abstract puzzle. It is a direct challenge to our most fundamental theories. It forces us to ask whether we need to rewrite quantum field theory, or reinvent gravity, or perhaps accept an even more radical idea, that our universe is just one among countless others in a vast multiverse. and we simply inhabit a rare bubble where this precarious cancellation miraculously occurred. Solving this catastrophe is the key to finally understanding what dark energy truly is, and ultimately, what drives the cosmos to grow. Even the most voracious objects in the cosmos are subject to its overarching rules. Black holes with gravity so intense that not even light can escape seem like the ultimate counterforce to expansion. Their powerful pull holds entire galaxies together, creating local pockets of order. Yet the question arises, could these cosmic anchors, in their vast numbers, also be subtly shaping the universe's growth? The answer weaves a fascinating tale of interconnected forces. While black holes dominate their immediate surroundings, their collective influence on the grand cosmic scale is a delicate balance. Some theoretical models propose a startling possibility. As the universe expands and black holes age, they might gain mass in a way that is intrinsically linked to the expansion rate itself. This process, where the growth of a black hole is coupled to the stretching of space around it, could generate a sort of pressure that contributes to the overall push of dark energy. In this scenario, the very fabric of the cosmos and its most compact objects would be engaged in a silent, symbiotic dance. The energy budget of the universe would then include a significant contribution from these dark giants, potentially offering an alternative explanation for the acceleration we observe, one that does not require inventing a completely new field or energy. To test these ideas, astronomers turn their telescopes to the hearts of galaxies. Observations of supermassive black holes, behemoths weighing millions or even billions of times the mass of our Sun, provide critical clues. Their growth histories, traced through the ages, must align with the broader narrative of cosmic expansion. If these black holes had gained mass too quickly or too slowly over cosmic time, it would leave a distinct imprint on the universe's structure, one that we do not currently see. The fact that their recorded growth fits within our standard models places tight constraints on just how much they could be influencing the expansion. For now, the evidence points toward a universe still dominated by the mysterious vacuum energy of empty space. The collective gravitational pull and any proposed energetic output from all the black holes combined appears to be a minor factor when measured against the overwhelming push of dark energy. They are essential characters in the cosmic story, but they are not driving the primary plot. This exploration reveals a profound hierarchy. The same expansion that carries galaxies apart also sets the stage for black holes to form and grow. Yet these local titans do not dictate the pace of the universe's grand journey. They are passengers on the expanding fabric, not its engineers. Recognizing this deepens our appreciation for the cosmos as a system of interconnected scales, where the most extreme phenomena are still woven into the same fundamental tapestry of growth. Time itself is a river flowing through the expanding cosmos, and its current is shaped by the stretching space it travels through. Our everyday experience tells us that a second here is the same as a second anywhere else, a universal tick of a cosmic clock. But general relativity paints a far more fascinating picture, where time is woven into the flexible fabric of space-time. The relentless growth of the universe does not just increase the distances between galaxies, it also gently tugs at the very flow of time. Imagine two identical clocks, one placed deep within the gravitational well of a massive galaxy where space is highly curved, and another left adrift in the vast, empty void between galactic clusters. The clock in the void, where space is expanding more freely, would actually tick slightly faster than its counterpart. This is because the expansion of space itself imparts a kind of stretch to time, a cosmological time dilation that runs in parallel with the redshift of light. When we observe the light from a galaxy billions of light years away, its journey is not just through an expanding space, but through an expanding duration. The light waves are stretched, making them redder, but the events we witness in that galaxy, like the slow flicker of a supernova, also appear to unfold in slow motion from our perspective. That distant explosion seems to take longer to brighten and fade than an identical one happening nearby. This is not an illusion, it is a direct consequence of the universe's growth affecting the passage of time over epic distances. We are essentially looking back into a past where time itself flowed at a different rate relative to our own. This cosmic relativity shatters the Newtonian idea of a single, universal clock ticking in the background of a static stage. There is no such privileged timeline. The moment of the Big Bang serves as our t equals 0, the starting point for cosmological time, but the subsequent 13.8 billion years have not passed uniformly for every corner of the universe. For observers in regions where space is expanding more rapidly, the flow of time relative to the cosmic beginning is different than for us, safely bound within our local galactic cluster. Thankfully, these effects are imperceptible on human scales, which is why our daily lives feel so consistent. Yet this hidden variability is crucial for understanding the universe on its own terms. It means that when astronomers peer into the deep field, they are not just seeing smaller, younger galaxies, they are witnessing a younger universe where time itself was marked by a different rhythm. This temporal dimension adds a profound layer to the expansion paradox. The universe is not merely growing larger, it is orchestrating a symphony where space and time are the interconnected musicians, their performance evolving together from a single, hot beginning to an uncertain, accelerating future. This vast cosmic architecture, a sprawling web of matter and emptiness, is the ultimate expression of the universe's growth. What we see is not a random scattering of galaxies, but a highly organized structure, a network of brilliant filaments and dense clusters separated by unimaginably large dark voids. This is the cosmic web, the largest pattern known to exist. It is a direct result of gravity patiently working over billions of years on the tiny seeds imprinted by quantum fluctuations during inflation. Think of dark matter as the invisible skeleton of this cosmic body. Its gravity provided the initial framework, the gentle hills and valleys in the early universe where normal matter, the gas that would become stars and galaxies, could slowly accumulate. As space expanded, these over-dense regions grew, pulling in more and more material, weaving the luminous threads of the web we observe today. The most striking features of this structure, however, are not the bright knots but the empty spaces between them. These cosmic voids are not simply gaps, they are actively expanding domains. Within these regions, there is very little matter to exert a gravitational pull, so the relentless push of dark energy operates almost unopposed. The voids are not just empty, they are growing, stretching faster than the universe's average expansion rate. This creates a fascinating dynamic where the emptiest parts of the cosmos are driving its acceleration most effectively, acting as engines of expansion that help push the surrounding filaments and clusters even farther apart. When astronomers create three-dimensional maps of millions of galaxies, they are essentially taking a snapshot of this cosmic web, a fossil record of the universe's expansion history. The precise distances between clusters and the sizes of the voids tell a story of how fast space has been stretching over cosmic time. This intricate design, a balance of dense congregation and vast emptiness, defies any expectation of randomness. It reveals a universe that is not just expanding, but sculpting itself into a coherent architecture through the eternal tug of war between gravity's pull and dark energy's push. This grand cosmic narrative, stretching from a fiery beginning to a cold, distant future, inevitably turns our gaze inward. We are left to wonder what our own brief, brilliant lives mean within such an immense and indifferent timeline. The universe's relentless expansion presents a stark philosophical challenge. If the ultimate destination is a silent, dark void where all structure and energy fade into uniformity, then what becomes of our human striving, our art, our civilizations, and our deepest questions? It can feel as if we are building sandcastles on a shore, knowing with certainty that an infinite tide will one day wash every trace away. This perspective suggests that on the longest of timescales, all meaning is transient, a fleeting spark in an unimaginably long and cold night. Yet this very same cosmic process, this expansion, is the very reason we are here to ask these questions at all. It was the initial rapid growth that planted the seeds for galaxies, and the subsequent, more measured expansion that provided the billions of years of stable quiet necessary for stars to forge heavy elements and for planets to form and foster life. The same force that points toward an eventual dissolution also created the narrow window of conditions for consciousness to emerge. Our ability to look up, to measure the redshift of distant galaxies, and to comprehend this vast story is itself a product of the universe's dynamic growth. This creates a profound paradox. The cosmos appears to be heading toward an end that, from a human standpoint, could be seen as the ultimate erasure of significance. Yet it is also a cosmos that has engineered its own self-awareness. We are the universe becoming conscious of itself. This leads to a pivotal debate. Does the lack of a cosmic happy ending imply that existence is inherently meaningless, or does our unique capacity to understand and reflect upon the COSMOS Chinese letter PURPOSE to the entire journey? Perhaps meaning is not something written into the stars for us to discover, but something we actively create through our curiosity, our wonder, and our relentless pursuit of understanding. The cosmos may not care about our legacy, but we do. The heat death is a scientific prediction, but it is not the entirety of our story. Our epoch, this brief sliver of cosmic time filled with light and life and inquiry, is vibrant and real. The expanding universe defies our common sense and stretches our comprehension to its limits, forcing us to confront existential themes on a scale we were never built to grasp. In doing so, it invites a deeper appreciation for the fragile, miraculous moment we inhabit. We find ourselves at a crossroads between scale and significance, between a cosmos of immense emptiness and the rich, inner world of a mind that can contemplate it. This is not a reason for despair, but a call to find value not in eternal permanence, but in the beauty of the temporary, and in the profound act of bearing witness to a universe so strange and magnificent. Our next leap into the cosmos is already underway, armed with tools of astonishing sensitivity. The James Webb Space Telescope peers deeper into the infrared than ever before, observing the earliest galaxies and the most ancient supernova to trace the expansion history with fresh eyes. Alongside it, the Euclid spacecraft is meticulously mapping the dark universe, charting the shapes and positions of billions of galaxies to reconstruct the invisible cosmic web and measure how dark energy has stretched it over time. Here on the ground, immense new observatories like the Vera C. Rubin Observatory will scan the entire visible sky repeatedly, creating a living, breathing movie of the cosmos that may catch subtle changes in expansion we have never seen. This multi-pronged assault on the unknown aims to corner the Hubble tension, that stubborn discrepancy in expansion rates, by measuring the universe's growth through multiple, independent channels. Scientists hope to see if the tension is a mere measurement error or a genuine crack in our standard model, a signpost to new physics. These missions will scrutinize dark energy's most fundamental property, its equation of state, to determine if it is truly a constant vacuum energy as Einstein hypothesized, or something dynamic that has changed over the life of the cosmos. The answer will dictate the universe's ultimate fate, locking in a future of heat death or opening the door to a more dramatic end. Beyond light, a new era of multi-messenger astronomy is dawning. Advanced gravitational wave detectors will listen for the ripples from colliding neutron stars, providing a direct, geometry-based measurement of cosmic distances independent of starlight. Deep underground, next-generation neutrino observatories will finally pin down the precise masses of these ghostly particles, clarifying their subtle but crucial role in the cosmic energy budget and its expansion rate. Each of these technologies acts as a different sense organ for humanity, allowing us to see, hear, and feel the universe's growth in ways previously unimaginable. They represent our species' collective drive to understand a reality that consistently defies our intuition, to solve a puzzle written into the fabric of space itself. The data flowing from these instruments will not just provide answers, but will undoubtedly pose new, even more baffling questions, ensuring that our journey into the expanding cosmos is far from over. Our journey through the expanding cosmos reveals a reality where common sense is not so common. We have traced the path from a universe thought to be static and eternal to one that is dynamically growing, a fabric stretching under the influence of a mysterious dark energy. This story, written in the redshift of ancient starlight and the faint whisper of the cosmic microwave background, consistently defies our earthly expectations. The grand structures of galaxies and the immense voids between them are not static monuments, but transient features in a cosmic river flowing outward. This relentless growth challenges our deepest intuitions about time, space, and our own place in the scheme of things. It invites a profound shift in perspective, from seeing ourselves as inhabitants of a fixed stage to recognizing we are participants in an epic, ongoing transformation. The darkness of the night sky is no longer an empty void, but a dynamic canvas, a testament to this grand expansion. Each pinprick of light we see is a message from a receding island of stars, carried away on the stretching fabric of space. This understanding does not diminish our world, but rather connects our fleeting moment of consciousness to the vast, evolving story of the cosmos. If this exploration has reshaped how you see the universe, consider subscribing for more journeys into the heart of space's greatest puzzles. We would love to hear which cosmic mystery captivates you most, so share your thoughts in the comments and let us continue unraveling